Good morning, everyone. My name is Nikunj Verma, and my roll number is IT2K2456, and my enrollment number is DE2402199. So today we'll be solving internal one question paper of our subject NAD. So in this paper, we have five questions. Question number one is simultaneous linear equations. Question number two is quadratic equation using floating point. Question number three is polynomial representation and its evaluation. Question number four is iterative methods for finding root. And question number five is associative and dissociative and distributive laws with floating point arithmetic. Yeah. So here is our question number one, which says write an algorithm or flowchart to solve the following pair of equations for x and y given in the values a, b, c, p, q, r, where equation is ax plus by is equals to c and px plus qr is equals to r. So this is our table. Here there are four cases. In every cases abc and pqr, the coefficient of two equations have different values, and x and y we have to find. And the A part of this question says comment on the results of case 1 and case 2 when there is a change of 0.001 is one of the coefficients. B says how interchange of equation affects the solution in case number 3 and case number 4. Revise the flowchart algorithm for solving the case when one or more coefficient are 0. So here we'll be using Gauss elimination with partial pivoting. So the algorithm is step 1 start, step 2 read coefficients. If A is equals to 0, swap equations, partial pivoting. If step 3, if any coefficient is 0, handle degenerate cases. Compute multiplier m is equals to p by a. Step 5, eliminate x from the second equation, where p is equals to p minus m dot a, which goes to 0. Q is equals to q minus m dot b. R is equals to r minus m dot c. Back substitute, will do back substitution to find the values of x and y equals is equals to r by q, and using y we will find x, where x is equals to c minus b dot y divides a. So here we will be getting x and y, and then we'll stop our algorithm. Solving all the cases by the algorithm, we will get x and y. The x is equals to 0.4516, y is equals to 0.9904 in case 1. In case 2, x is 0.7077, y is 0.8553. In case 3, x is approximate to 0 and y is 1. In case 4, x is 2 and y is 1. So worked calculation for case is equals to 1, we got we get m is equals to 1.251 divides 2.5, which is 0.5004. And now new q. So the new q will be getting according to formula 2.605 minus 0.5004 into 5.2. We will be getting q is equals to 0.003. Similarly, we will be getting r is equals to 0.0495. Using this, we'll be getting y is equals to 0.0495 divides 0.003. So we'll be getting y is equals to 0.994, and using y we'll find x is equals to 0.4516. Now analysis. In case 1 and 2, change of 1q 0.001 in q. Case 1, q is equals to 0.605, then x will become 0.4516 and y will become 0.9904. In case 2, q will become 2.606, then x will become 0.7077 and y becomes 0.8553. So x changes by plus 57% from a tiny change of 0.001. Here we can see when q is changed just 0.001, the x is increased by 57%. So determinant is equals to AQ minus BP, which is equals to 0.0073 near 0. Thus determinant is ill conditioned system. Large condition number is becomes unreliable results. Remedy: we will be using higher precision and scaled pivoting. So we'll be going on to the B part, how interchange of equations affect the solution in case 3 and case 4. Solution case 3 and 4 when equations interchange. Case 3 m becomes 50,000, which is catastrophic, and in case 4 after row swap 0.00002, which is stable. Always pivot to the largest coefficient. Revise algorithm when one or more coefficient are 0. So we'll revise the coefficient by when a is equals to 0 but p is not 0, the swap rows. When a is not equals to 0 but p is 0, no swap, proceed normally. If a is equals to 0, p is equals to 0, print no unique solution. B or q is equals to 0, then check for consistency. If r is equals to 0, then one solution may be trivial. Now case-wise behavior. In case 1, graphic natures for lines were intersect at large angle. Case 2, lines nearly parallel. Case 3, one line almost flat. Case 4, better orientation after interchange. Now the second question is quadratic equation floating point roots. Consider the equation x square plus 2x minus 2. Obtain roots and floating point with 4 digits in mantissa. Substitute the roots in equation. Comment on satisfactorability in both of the cases x1 and x2. So here is our cases, case 1 and case 2. Problem solve equation efficiently with high precision. Objective: we'll be using Newton-Raphson method to compute the roots and floating point. X n plus 1 is equals to xn minus f of xn for f dash of xn. So for a given equation f dash x is 2x plus 2. We'll iterate this method for the root. For the first root, we'll take a guess x is equals to x0 is equals to minus 3. At iteration 1 we'll get fx dot 1. At iteration 3 we'll be getting fxn is equals to 0. Thus our xn becomes point. Here in the third iteration we'll be getting fxn fx, which is approximate to 0. Then we'll be getting our root x minus 0.2 minus 2.7320, and for the second root we'll be taking another guess x naught is equals to minus 3. So on the third iteration our root becomes 2.7320. So yeah, our roots are correct. Graphical analysis: x1 is equals to 0.7320 and x2 becomes minus 2.730. So both roots satisfy equation with high accuracy achieved with few iterations. Curve intersect at x-axis at x is equals to 0.732 and x is equals to minus 2.732. Newton method converges in tangentially to roots. Thus Newton-Raphson method provides us results with in less number of repetitions. So question number 2 is computation table and satisfactorability check. In case 1, x1 becomes 0.7320, then it is approximate to 2, thus it is precise within 4-digit mantissa. Key observation: catastrophic cancellation. When computing x1, subtraction of nearly equal number causes loss of significance. This is cancellation error. Better formula for root x1: use x1 minus x1 is equals to minus c divides a dot x2 is equals to 2 divides a into minus x2, which is the root, minus 2.732. So x1 becomes minus 0.377320. Conclusion: order of parenthesis changes, rounding sequence, different rounding errors. With 4-digit mantissa, results are reliable, but for ill conditions cases, grouping matters. Polynomial representation and evaluation. So another illustration of our formation of the recurrence relation will consider the problem of dividing a polynomial where r is the root of the original polynomial. The long division method is illustrated below. We'll do long division to find the reduced polynomial. In general, we'll get the method we'll be getting this b n minus 1 is equals to a n. So due by this we can get this, and using this we can obtain b n minus 3 is equals to a n minus 2 plus r into b n minus 2. In general equation we will write b n minus bracket में I plus 1 which is equals to a n minus 1 term plus r dot b n minus I term. The above recurrence relation is expressed in the following algorithm. For I is equals to 0 to n, in steps of 1, we'll read a term, we'll read all the values of a. If a n is less than equals to b n minus 1, for I is equals to 1 to n minus 1, we'll again start a loop. Then we'll be checking the condition b n minus plus I n minus bracket I plus 1th term is less than a n minus ith term plus r dot b n minus 1th term. For I is equals to 0 to n minus 1, we'll again start a loop. Then we'll write b, and then we'll get the values of b and we'll stop the algorithm. Iterative methods for root finding: dissection, Newton-Raphson, secant, convergence, and reliability. These are the 4 methods, and we'll be discussing the convergence. So in bisection, the iterative formula is this. Its order of convergence is 1 bit per iteration. Evaluation of function per iteration is 1. Reliability of convergence, it gives guaranteed convergence. False position, method of false position, the formula of method of false position is this. Order of convergence is 1. Evaluation of function per iteration is 1. It gives guaranteed convergence. Newton-Raphson's formula is this. Its order is 2. Its evaluation of function per iteration is 2. No guaranteed convergence. It's not reliable. Secant, it gives 1.62 order, and function per iteration is 1. No guaranteed convergence. Successive approximation, formula is xi is equals to g of xi minus 1, and order of convergence is 1. Evaluation of functions per iteration is 1. No guaranteed convergence. Method overview. So flowchart and convergence analysis. In Newton-Raphson flowchart, we'll take input fx and f dash x, x naught, e value which is 0.001, 0.0001, and we'll take the maximum iteration. We'll compute fx and f dash x. If f dash x is less than the 0.0001, which is e, then we'll take yes, print derivative 0, method fails. X1 becomes x0 minus fx divides f dash x. If f is x1 minus x0 is less than 0.0001, then yes, print x1 is the root. Is iteration is greater than max iteration, then we'll say no convergence, we'll stop the loop. X1 is equals to x1, iteration is equals to iteration plus 1, loop back. We'll iterate loop once again and increase the count of iteration, and we'll always check the iteration, number of iteration as the given input. Error convergence in Newton-Raphson's method, from x0 is equals to 1.5. Iteration 0 will get error of 0.0858. In iteration 1 we will get error of 0.0025. In iteration 2 we will get error of 0.000026. Conclusion: Newton-Raphson double digits of accuracy each iteration. Bisection half the error, nearly safe but slow. We'll use bisection to get close, then Newton-Raphson to get the efficient answer. So we'll move on to our last question: associative and distributive laws in floating point. Verification with 4-digit Mantissa, no truncation. Problem statement and theory. Floating point arithmetic key facts. Real numbers are approximated with finite Mantissa digits. 4-digit Mantissa means fx is equal to x dot 1 plus e. E is less than 0.5 into 10 to the power minus 4. laws being verified, associative law, a plus b whole bracket plus c versus a plus whole bracket b plus c should be equal in exact arithmetic. Distributive law, a multiplies whole bracket b plus c versus in bracket a into b plus in bracket a into c should be equal in exact arithmetic. Why this law may fail in floating point? Addition of number of very different magnitudes cause small values to be lost. Grouping determines which addition happens first, defining different rounding on each step. Given values are a, b, c, and on the set 2 a, b, c are given as this. Verification of set 1 using associative law will get LHS is equals to 11.365 and RHS 11.365. So here LHS equals to RHS, which holds here, and observation B. B is small relative to A. If Mantissa were 2-3 digits, B would have been observed. Law would fail. But the B was very small. Then law was justified. Now we'll verify distributive law for the ABC of the given set A1. Here B plus C becomes 5.7 and LHS becomes 32.29 and RHS becomes 32.28, which is rounding error. So there is a difference of 0.01. So conclusion, distributive law does not hold exactly the same floating point arithmetic, because when we multiply, a loss of more significant digits happens. The grouping of operation determines how rounding errors accumulate. Now for the set 2, values of ABC will verify associative law. LHS A plus B whole bracket plus C becomes 10.14 and RHS becomes 10.14. Thus again law holds, but B is very small. In 3-digit Mantissa, B would be dropped. Distributive law, A cross B plus C plus AB plus AC. B plus C becomes 25.4, which is LHS. RHS becomes 25.44. Here LHS is equals to RHS. Distributive law holds for set 2. Less rounding error because magnetics are closer to each other than set 1. That's why it gives less error. Summary of floating point arithmetic laws. Set 1 associative worked but distributive failed. Set 2 associative law was verified but distributive law was not verified. Key conclusions: arithmetic laws do not always hold in floating point arithmetic. Violation is caused by rounding at each arithmetic operation. Numbers with different magnitudes cause absorption error. Using more Mantissa digits in reducer never eliminates those errors. The order of computation matters. This grouping that minimizes magnitude difference to reduce rounding error. Practical rule: always add numbers of similar magnitude together first. Avoid subtracting nearly equal numbers. Use double precision, 8-byte float or 15 digits for sensitive calculations. Summary: in the question 1, we used Gauss elimination. In question 2, we used quadratic formula, 4-digit Mantissa. In question 3, we used long division. In question 4, we compared the different root finding methods. In question 5, we compared the floating point verification and we verified the laws about that.